In this video, we're going to examine the effect of structure on acid-base properties. So, let's look at some generic acid, HX. In order for this substance to be an acid, this HX bond must be polar with the hydrogen having a positive charge or partial positive charge, and the X having a partial negative charge. So in something like an ionic hydride, that bond polarity is reversed. So our HX bond is polar with our hydrogen having a partial negative charge, and our X having a partial positive charge. In this case, our substance is going to act as a base. Remember that hydrides are strong bases here. So, other important factors here in determining the acid strength include the strength of our HX bond. So, if the HX bond is really strong, then we can't break it. If the HX bond is weak, then that bond can be broken. We have to be able to break this HX bond. If that bond is too strong, then that proton is not going to act as an acid. So the weaker that bond is, the stronger of an acid this HX is going to be. The other thing another thing to take into account is the stability of our conjugate base, X minus. The greater our stability of our conjugate base, X minus, the more acidic our HX can be. Because if X minus is really unstable, if it's really energetically unfavorable for that X minus to be around, then that H plus is not going to come off the molecule. It's going to stay together. It's not going to dissociate. But if that X minus is really stable, then we have a thermodynamic driving force for our bond to be broken. So for binary acids, then this HX bond strength is important in determining the relative acid strength in any group on the periodic table. So the HX bond strength tends to decrease as the element X increases in size. So as we move down on the periodic table, that bond strength is going to get weaker, which means that acid strength is increasing as we move down a group. So as we move from HF to HCl to HBr to HI, the HF is a weak acid. HCl is a stronger acid. That's one of our strong acids. Remember, HF was not one of our strong acids. HBr, hydrobromic acid, that's an even stronger acid than hydrochloric is. And hydroiodic acid is a stronger acid than hydrobromic is. Because as we move down, the size of our element is getting larger, which means that that HX bond is getting weaker, and that means the acid must be getting stronger. What this also means is that base strength is decreasing as we move down a group. So a chloride ion is a stronger base, although still negligible. It's a stronger base than a bromide ion is, which is a stronger base than an iodide ion is. But the chloride ion is a weaker base than the fluoride ion is. Remember, fluoride, hydrogen fluoride, hydrofluoric acid, is a weak acid, which means its conjugate base, fluoride, must be a weak base. Whereas with hydrochloric acid, HCl is a strong acid, which means that its conjugate base, chloride, must be a negligible base. Chloride is a negligible base, but fluoride is a weak base. So the base strength is increasing as we move up the group. So this HX bond polarity is also important in determining the relative acid strength in any period of our periodic table. Note that on the last slide we were talking about groups, which are the vertical columns. Now we're talking about periods, which are the horizontal rows. So electronegativity is increasing as we move to the right on our periodic table. It's decreasing as we move to the left. So this bond polarity is increasing as we move to the right. And that means that acid strength is increasing as we move from the left to the right. Because the more polar that bond becomes, the easier it's going to be to break that bond. And that means the base strength is decreasing as we move from left to right on the periodic table. So let's look at HF. That HF bond is highly polar, and this means that HF is acidity. But both hydrogen and fluorine have small atomic radii, and this means that that HF bond is very strong. This means that HF is a weak acid. Remember that hydrogen fluoride can undergo hydrogen bonding, whereas something like hydrogen chloride cannot. And that's because in order to undergo hydrogen bonding, you have to have a very electronegative atom, and it's got to be relatively small. So it only happens when you have a hydrogen atom bonded to a nitrogen, an oxygen, or a fluorine. That's it. So HF can undergo hydrogen bonding, and that means it's a weak acid. It's not a strong acid. Let's look at another one. We have methane, CH4. That hydrogen-carbon bond is almost nonpolar because the electronegativity difference between hydrogen and carbon is relatively small. It's only 0.35. The difference between hydrogen and fluorine is more like 2 or thereabouts for the HF. This means that our hydrogen-carbon bond is rather strong because both atoms have strong atomic radii. And these two combined, the relatively low polarity and the relatively small sizes, which means that it's a strong bond, means that methane is neither going to act as an acid nor a base. So now let's look at oxyacids. So oxyacids are acids that contain one or more oxygen-hydrogen bonds. So acids that contain OH groups and often additional oxygen atoms bound to our central atom. These are what we call oxyacids. So all oxyacids have some general structure like YOH, where we have something like this, where we have nitric acid, and we have our nitrogen atom in the middle bonded to 3 oxygen atoms, one of which is bonded to our hydrogen atom. So the strength of our acid here depends upon Y, our central atom, and the other atoms attached to Y. So how many other oxygens are attached? If you have some other atoms bonded to our central atom Y, those matter as well. So as the electronegativity of Y increases, so does the acidity of this substance. Basically, go back. If we put something in here that is more electronegative, that's going to be pulling on the electrons it has shared with the oxygen more strongly. As that central atom is pulling more strongly on those electrons, and the oxygen pulls more strongly on the electrons with the hydrogen, that weakens that oxygen-hydrogen bond, and that makes the acid stronger. Also, the bond polarity increases, and the stability of the conjugate base increases as well. We can summarize how acid structure relates to the electronegativity of Y and the number of groups attached to Y. So for oxyacids with the same number of OH groups and the same number of oxygen atoms, the acid strength increases with increasing electronegativity of our central atom, Y. So if we have something like HClO, this is hypochlorous acid, compared to HBRO, hypobromous acid, and HIO, which is hypoiodous acid. The atom with the larger electronegativity, the acid with the larger electronegativity of the central atom, so that's the HClO, hypochlorous acid, is going to be a stronger acid than this one, which is a stronger acid than that one. So now let's look at oxyacids with the same central atom, Y. Acid strength increases as the number of oxygen atoms attached to Y increases. So if we have something like perchloric acid, that's going to be stronger than chloric acid, which is stronger than chlorous acid, which is stronger than hypochlorous acid. And again, this makes sense because as we bond more oxygen atoms to that central atom, those oxygen atoms are pulling more electron density away from that central atom, which means that central atom is going to pull stronger on the oxygen that is bonded to the hydrogen that oxygen then pulls more strongly on the electrons in between it and the hydrogen, and that weakens that oxygen-hydrogen bond, and that makes the acid stronger. So, which one is a stronger acid then? Sulfuric acid, H2SO4, or sulfurous acid, H2SO3. I want you to pause the video and think about it. So, the stronger acid is one with more oxygen atoms bonded to the central atom. That's going to be the sulfuric acid. Sulfuric acid is one of our strong acids. Sulfurous acid is not one of our strong acids. So, now we can talk about carboxylic acids. So, there are many acids that contain a COOH group, which is what we call a carboxyl group, that looks something like this, where we have a carbon atom double bonded to an oxygen. That carbon atom is also singly bonded to an oxygen, which is singly bonded to a hydrogen. So this group here is called our carboxylic acid. Note that we've got the same group here, and we've got the same group there. So in each of these cases, we have a single bond to something else. In this case, it's a methyl group. In this case, it's a benzyl group. In this case, it's just a hydrogen. And so, acids containing a carboxyl group are called carboxylic acids. So here we have acetic acid. Here we have benzoic acid. Note that this acetic acid is vinegar. And here we have formic acid. Why are these molecules acidic? This additional oxygen atom on our carboxyl group, this double bonded oxygen, is increasing the polarity of our oxygen-hydrogen bond, and it's stabilizing our conjugate base through resonance. So our carboxylate anion exhibits resonance, and this resonance gives it the ability to delocalize that negative charge over the carboxylate group, over those two oxygen atoms and the carbon, which increases the stability of our conjugate base. Anytime you can increase the resonance, you're increasing the stability of the molecule. Remember, as we increase the stability of our conjugate base, our acid is getting stronger. The acid strength also increases as the number of electronegative groups in the acid increases. So if we have something like acetic acid, like this, it's significantly weaker than the trichloroacetic acid, like this. Basically, we replace each of those hydrogens with something that is significantly more electronegative, like chlorine. Each of those chlorines draws more electron density away from that central carbon than the hydrogens do over there. And that draws more electron density away from this carbon, which draws it away from that oxygen, and that makes that bond weaker. So trichloroacetic acid is a stronger acid than acetic acid is. So that was the effect of structure on acid-base properties.